Okay, by now you guys know that the TensorFlow has this graph underneath. Okay, first question comes, why do you need a graph? Right? Why you don't just use your programming language, build the parse tree, and just use that? And the reason is because a meta graph, you can distribute it. You can precisely say where each computation is going to go. Now, we know now we have three different kind of devices, right? We have CPU, we have a GPU, and last week we have a TPU. Okay, so suddenly this representation becomes very useful because you can take one of the nodes and specialize specifically for that kind of process. Okay. So how does it work very high level? This representation, these are different nodes on different machines. Okay, so we have different machines, and on each of these will spin up our TensorFlow process. And the way they communicate is with this new library, gRPC. RPC is a remote procedure call, so you are able to invoke a method on another server. We have HTTP2 as the connection link, so we don't have the latency of setting up the connection, waiting that the TCP is ready, sending something, and then closing the connection. With HTTP2, the connection is open. You just stream back and forth the data. And it's bidirectional too, so that's very important to, if you're moving big tensors, like big matrices, like in a neural network, it's very, very convenient. You save a lot of time. So anything that is between processes, of course, has to be serialized. And Google already implemented something called protocol buffer, and they actively use it. And anything that has to be exchanged has to be serialized. Okay, so for everything, every main object of the framework, there is a protocol inside the source code that you can look at that and see exactly what is being transmitted. And we can look at some files later. We dig inside the code. So there is some terminology that at first glance can be confusing. We'll try to make it more confusing. So mainly we have a cluster. A cluster is made of jobs, and each job has a series of tasks. Okay. We usually specify the cluster in what is a cluster specification. The jobs usually are two. One is for parameter server, and one for the worker. And then for each of the jobs, you have different tasks. So it's just a list. So 0, 1, 2, 3. They don't have a particular name. But the jobs' names are important because as you can imagine, the worker will actually execute the computational nodes of the graph. But in some algorithms, you need to share some of the variables. How you will do that? You will have a parameter server. So for who of you know neural networks, you have the gradient descent step, okay, and that value have to be consistent among different nodes. Okay, so you have let me go back. So imagine you have this 3-node cluster, and you have your graph, and you want to compute one step of your feed-forward neural network. What we will do, we will move the data and the graph on the different nodes, compute, do the gradient descent step on the 2 different parallel nodes, aggregate back the gradients. It's going to do an average of the values, and then it will redistribute the gradients. Of course, this works and is valuable if this step is much more compute intensive than transferring the data, right? And now you have a bit of big shift from big data back to big computation. If transferring the data takes more than your computation, there is no point in transferring the data. OK, now let's get practical on an example of cluster specification. So in this example, we have a parameter server. There is written very little at the end of the tutorial why PS is parameter server. And then you have a set of workers. So this is the job. OK, we have this job, and we have one task. OK, and this is another job, and we have 3 tasks. And when we launch the process, we have to indicate, given a cluster spec, what is your job and what is your task. And inside the cluster, you can only have one that has that task. Okay? You can have 2 nodes with the same task. That means no 2 nodes can have worker, be a worker, and have task did 0. Okay? So the most simple thing that you can do is this program, where it creates a local server. So you have 2 processes in your local machine, one that it has a server and one that it has a session. Okay? And this session will communicate to this server on the same node. So how many jobs do we have in this? Hello? So we have 1 job and 1 task. Okay, very simple. And you have a bit of the magic going on here, where the session is going to take this tensor. In TensorFlow, everything is a tensor or an operation, but you just move around tensors. It's going to execute. The session it knows where are the worker server. It's going to send the graph. In this case, the graph consists only of 1 operation that is a constant operation. It's just give me back 1. Execute and get back the values. OK, this is much clearer with this graph. OK, so other cases of using a distribute setting. Now, why you will really need this distribute settings. One is training. OK, this is most of the time what we need, having 1,000 of machines, because you can parallelize a lot of this problem. Another case is hyperparameter optimization. And if you have read online Spark integration, they started using this one, because we will talk later of how you can use TensorFlow and distributed computing. And then we will look very briefly at ensembling. OK, so this is a graph that I created for trying to understand what are the components if you have to go down in the TensorFlow space. So we saw already the server. We have the cluster specification. No? We know which workers and which task. So we have the device, the specific CPU, TPU, and GPU. And then we have the session. So the session, you can think and abstract it as maintaining the state of a graph. Once you run, there are some side effects. And the session maintains in memory what's going on with all those variables. OK? Then we will talk about the supervisor. Supervisor is the object to use. It's not very well marketed, but has a lot of good stuff. And the session manager. Coordinator and server are coordinator is for the threads, and you don't really need to know much what's going on. And the server is to save the state to disk. OK?
Fabrizio?
Yes?
Okay, so which ones are actual separate nodes? Or this is...
So there is nothing of the graph here. OK, this is what...
Sorry, for like workers, I guess. Like this is...
Yeah, so it would be a combination between the server and the session. Has some state inside that allows you to run the graph.
Does the supervisor, like that's its own worker?
No. This is how the process is when you create the nodes. When you create these nodes, that's what is being what is being created inside the process.
And but by node you mean like worker node?
Worker node, like process in a machine.
TensorFlow.
Non an operation on the graph, yes. Told you I'm going to confuse you more. So this is a good object to know. It's the session manager. And one thing that you want to do is checkpointing. Okay, so you have your session. Usually this thing runs for from some hours to weeks. Okay, you don't want the cat coming by and just crashing the machine and you lose 1 week of training. So one way is to manually set up all the checkpointing and make sure all the variables are right and all of that. And other way is to just use the session manager, and it's gonna save the checkpoints periodically after a certain amount of steps and runtime. And the other object that is very good is the supervisor. And this also sets up a session manager inside. So it also handles some other things when you're using a distributed graph. So if for some reason one of the nodes crashed and it cannot recover, it will shut down gracefully. This is one parameter you have to keep in mind when you want to run the graph. This has to be the main graph, the main node that runs all the other node in the cluster. So details that you have to go inside and try to play. There is not much documentation about this, but this is very good to actually see how to use these classes. Yes.
So wait, but if the chief dies, that worker.
Yes, if the chief dies, you have already the checkpoints. So you have to rerun and rerun the checkpoint from the same. No, if the chief goes down, you have to restart, saying, "Oh, the chief is the one that died." Okay. So there are two ways of doing the training. One is synchronous and one is asynchronous. The nice thing with asynchronous is all your nodes just keep iterating over the graph without actually communicating between each other. The downside is sometimes some of the nodes will go lag behind the others one. No, will not be at the same speed. For whatever reason, maybe it's a cloud service or one of the machine is older. And so the variables will start not being updated at the same time. And this can influence the training speed. And that's why it's useful to have synchronous training. It's, of course, slower than the other, but it gives more consistent result. And there is this train synchronized replicas optimizer that will create a graph such that it will synchronize all the other subgraph in time before doing the second step. No? So it will go one step across all your network, collect all the variables, make sure every node completes, compute locally the update, and send back all the updated variables across the cluster. This is another handy tool that you can use. As I said before, you can specify exactly where each variable is in the graph. Okay, so this is our cluster. We have this is a job, parameter server. We have two tasks, task 0 and task 1, and we have one job that is worker, and we have two tasks. Okay, with this syntax, with TensorFlow device /job ps /task 0, we are saying that these weights and these biases will be handled on this node. Okay, so every update, it will be sent to this node. And same with this other nodes. So you have, for example, task 0, and I color-coded just to make you help on the association, right? So imagine this is a very simple model. Now imagine if you have 10, 20 variables. Imagine if your cluster changes. It's pretty much daunting to go there and set it up manually, all these variables. What you want to do instead is just use a very simple strategy, and is the replica device setter. And this will, given a list of tasks in one of your parameter server, for example, it will assign one variable to a different task in sequence. So variable 1 to task 0, variable 2 to task 1, variable 3 to task 3, variable 4 back to task 0. So in a round-robin fashion assignment. So there are different configurations that you can do. Usually you want to be either synchronous in graph, this is the easiest way. We're having one graph and everything is synchronous. Or you can have between graph asynchronous, where you have different graph running parallel, and then you try to synchronize on the same node. And this is the example with the replica device setter. It will be variable 1 assigned to task 0, variable 2 task 1, variable 3 back to task 0, because we have only 2 tasks. I can show very quickly. So this works, of course. But to prove you, so this is a very simple setup. I have Chris put up three instances on Google Cloud, and just basic Linux instances, and run 3 gRPC server, and then I run this other script. You can really read that it will connect to the cluster and start training, and then I can run another one.
Can you zoom in?
I think so. Okay. And so this, I will run another one, and this it has worker index 1, while the other one has worker index 0. And so you will see that this started with a global step of 43. Okay, so they are sharing what's the global step, and they're trying to synchronize. And the nice thing, you had to only define the cluster. Okay, that's the very powerful thing, because you don't have to manually set up every single connection, maintain the TCP, and all of those steps that you had to do before. So I'm going to show real quick what's the what is it? So I want to show you real quick what? I love that. So this is the graph of the script that is running right now. Okay, so it's pretty complex. And as you see, it's very detailed. So you can recognize some of the name of the variables. So global step, hidden W, hidden B, beta, truncated normal. And these are from this script. Now, if you, and this me and is replica, I'm gonna. Okay, so it's a pretty involved program. This is how to train MNIST. That's the basic ABC of neural network using distributed TensorFlow. And you can find this example inside TensorFlow/tools/dist_test/Python. I know, like, but that's why you're here, because I found it, and it's very hard to find it, even if I look at the Git repository every day and understand what it actually does. So some highlights here. You will recognize the device setter. Okay, so you will see try and replica device setter. It will do some. It will create the cluster specification. Okay, PS and the worker. It will do other setups. Create a variable. It has a global step. Remember to anything that is not trainable, that you just needed to coordinate the graph, you have to set it trainable as false, because otherwise it will try to do some operation and it will blow up. Yes, we see the sync replica optimizer that we saw it before, and then this is using an Adam optimizer that currently is one among the best. We have the supervisor, is chief. You guys already know all of this function. And then other machinery to make all this system work. I'm going to go real quick on the hyperparameter optimization. So all of these algorithms, as you saw, for example, in the optimizer, they have other variables, right? What is it? For example, learning rate, but each optimizer can have other parameter to tweak in the way they optimize your graph. So how do you find what are the best options for those algorithms? Use hyperparameter optimization, okay? And last is ensembling. So a very nice trick is to improve your performance of your models. Is just you train different models with different maybe just initialization weight and different parameters, and then you ensemble them. So you make them run all at the same time with the same input, and then on the result of those different models, you choose the one that is best. Okay. Yes, yes. This comes from statistic, where by properties of the approximator, the sum is better. I didn't have the time to actually saw with the other framework. One little last thing I want to show you is what the neural networks actually look like. So this is from inception, actually, one of the layers of the neural network. This is after being trained. Okay, so what are those values? It's trying to get an interpretation of what's going on in the image. Okay, these are just the weights after being trained, and I find them very interesting. No, there is some appealing in the image that we synchronize somewhat with the result. No, they are such a primitive pattern that we must have something similar